Hello everyone, welcome to the fourth lecture of the series on AI using Python. In this lecture, we discuss the basic concepts and illustration of linear regression, which can be considered as the simplest regression algorithm. In linear regression, we fit the input-output data with a linear function or model. This means a line in the case of univariate input-output data and a hyperplane in the case of multivariate input-output data. And in general, the linear input-output model can be defined as in this equation, where a and b are scalars in the case of univariate data, which corresponds to the slope of the line and intercept of the line. And for multivariate regression, a will be a matrix of size m by n, where n is the number of input variables and m is the number of output variables, and b will be an m-dimensional vector. In general, we call a and b as the weight term and bias term. And now in linear regression, our objective is to find the optimal weight a and bias b for a given input-output data. And for that, we can use the available data or the training data, which consists of n observations of the input samples, which we denoted by x1, x2 up to xn, and n observations of the outputs, which we denote by y1, y2, yn. So here this capital N denotes the number of observations in the data set. In the case of linear regression, the model will be a linear function, and for univariate case, the model f will be mapping from the set R to R, where R is the set of real numbers. And in multivariate case, the f will be a mapping from the set Rn to the set Rm, where small letter n is the number of input variables and small letter m is the number of output variables. Now, in the case of linear regression, we can have an analytical solution for finding the best values of a and b, which can be derived using the ordinary least square approach. In this lecture, we are not going into the derivation of the solution. Instead of that, we will illustrate how to solve linear regression problems in Python. And for illustrative linear regression, we are considering an example in which the training input consists of 100 equally spaced data points between 0 and 10, and the training output data is generated using this linear relationship, where ytr is equal to 3 into xtr plus 2 plus r, where r is a Gaussian random variable with mean 0 and variance 1. Now let's move on to the code. And in this example, we will be using functions from NumPy, Matplotlib, and sklearn libraries. And in specifically, we will be using the linear regression function from the sklearn library to fit a linear model to the input-output data. Here, we generate the input-output data using a linear function, and the input data x consists of 1000 equally spaced data points between 0 and 10. And the output data is defined as y is equal to ax plus b, where a is chosen as 3 and b is chosen as 2, which gives y is equal to 3x plus 2. Here we consider this as the actual model, and this output is considered as the actual output, and this value of a and b can be considered as the actual parameters in the model, which are normally unknown. Then we can add some randomness to this data to generate the training data, and for that we use the random state function from the NP library, which is used for generating random numbers. Then the training data XTR consists of 100 equally spaced data points between 0 and 10, and the training data YTR is defined as A into XTR plus B plus R, where R is the random variable. Here len of XTR will be 100, so this will be basically an array of size 100, where each element is a random variable generated using this function. We can plot XTR versus YTR, which gives the training data as shown in this figure. Now, our objective is to find a linear model or a line that fits this input-output data in the best possible way. For that, we can use the linear regression function from the sklearn library, and here we rename it as model. Then we can find the parameters in our linear model by training the model using the training data XTR and YTR. And for that, we will be using the fit function. Then we can predict the output data for the input X using the predict function, and we denote the predicted output as y underscore L. where this L stands for linear regression. So this y underscore L is the predicted output, or y hat in our case. Then we can plot the training data xtr versus ytr, and the actual data x versus y, and the predicted data x versus yl, which gives the plot as shown in this figure. Here, this red dot corresponding to the training output data, and the black line corresponding to the actual output data, and this green line corresponding to the predicted output data. Here we can see that the output predicted using the trained model, which is the green line, closely matches with the actual output, which is the black line. Now we can also find the parameters of the model, which are the slope and intercept of the line, and for that we can use coefficient underscore and intercept underscore command, which gives the slope as 3.03 and the intercept as 1.89. In the actual model, we have selected the slope or the value of a as 3 and the intercept or the value of b as 2. And here we got 3.03 instead of 3 and 1.89 instead of 2, which are sufficiently accurate. This means that we were able to learn a linear model using the training data, and here we have considered a univariate regression example. We can also fit a linear model to multivariate data, which results in hyperplanes in the input-output space. And such examples will be discussed later on in this lecture series. In the next few lectures, we will be focusing on nonlinear regression and various algorithms in their category, such as polynomial regression, logarithmic regression, neural network regression, etc. With that, we come to the end of this lecture. Thank you.